Hey everyone, it is Mr. Vargas here, back once again, looking to help out Math 3 with homework 7.3, graphing reciprocal functions. I hope you guys had a great spring break and you are ready to get back into high gear. So let's get started with today's homework assignment, 7.3, graphing reciprocal functions. Now the key things that I want to highlight here in this video involve vertical asymptotes, and not only that, also horizontal asymptotes. Okay, so pretty much what we need to do in order to figure out where vertical asymptotes are is we need to identify x values for which f of x is undefined. And what we mean there is we cannot have no zero in the denominator. Okay, so no zero in the denominator. That is where our vertical asymptote is going to occur. Whatever value causes that denominator to become zero, you're going to get that vertical asymptote. And we usually represent vertical asymptotes with dashed lines, straight up and down. Horizontal asymptotes, this is usually f of x equals 0 for reciprocal functions, unless we do some type of shift, some type of vertical shift, up or down. And we'll look at some examples of that. And remember, a horizontal asymptote will use dashed lines again, and it'll go side to side. Okay, awesome. Let's check out number 2. We've got this function f of x is equal to negative 3 over x minus 1. Remember that our parent function is actually f of x equals 1 over x. So if you just want to see how this has been changed, well, we've multiplied the top by negative 3, and we've also subtracted away 1 from the bottom of our parent function, and that has caused it to come out like this. Here, we are asked to identify the domain, the range, and where our asymptotes occur. So first things first, let's find those asymptotes. And the first vertical asymptote is going to be at the line right here, and that is x equals 1. So, and that kind of makes sense because what happens when I plug 1 in for x? 1 minus 1 makes 0, so that's definitely where our vertical asymptote occurs. So let's do VA at, we'll say x equals 1. So that line, x equals 1, is our vertical asymptote. Now we want to know our horizontal asymptote, and here we did not do any type of vertical shift. We didn't do a plus something or a minus something on the outside of our original function. It would usually be right here, that's our k. So here our horizontal asymptote is just actually right across the middle at horizontal asymptote at f of x equals 0. So that's our horizontal asymptote. Okay, now if we want to do domain and range, let's do domain. Well, domain is going to be all of our x values, and it goes from negative infinity all the way up to 1, and then it starts back down here and goes all the way to positive infinity. So here the way we could write this domain, since we're going left and right, remember domain is our x values going left and right, we would say that x is in the element of R such that x does not equal 1. Okay, and that's some set notation right there. So domain is x is all real numbers, but we have the stipulation that x cannot equal 1. Okay, now our range is going to be all of our y values, or our f of x values, going up and down. And here, if you follow the graph, you can see it's going to go to positive infinity, going up this way, and it's also going to go down to negative infinity, going this way. The only place where we don't get a y value is on this horizontal asymptote at f of x equals 0. So here I can say that y, our y values, or our f of x values, are also in the element of R, such that y cannot be equal to, this time, 0. That's where our horizontal asymptote occurs. Okay, moving on. Let's go down to the next page. And here on this second page, we've got some important key concepts. We've got equation form for a reciprocal function. It's f of x equals, we've got some number a over our variable x minus or plus some number h, and then on the outside we have the plus k. This h represents your shift left and right, so how your function moves left and right, and this k represents your shift up and down, similar to the other types of functions that we've worked with so far this year. Alright, if we want a horizontal translation whenever we move our function left and right, the vertical asymptote will actually move left and right by that h number. So you can imagine our vertical asymptote is like this, and then if we move it right, it goes over here, or if we were to move it left, it would go somewhere over there. Okay, so whenever we have a horizontal shift, that moves our vertical asymptote. And similarly, whenever we have a vertical translation or a vertical shift, the horizontal asymptote moves to y equals k. And that would be this right here. This is our vertical shift. So you can imagine the asymptote, starting here, and then sometimes it'll shift down or sometimes it'll shift up, depending on that value of k. Alright. Now we can also reflect our reciprocal function across the x-axis, and that happens when the a value is negative. So if this value right here is ever negative, it's going to cause your graph to flip over the x-axis. And then the last thing, compressing and expanding. The graph is compressed vertically when you have a fraction, whether that be a negative or positive fraction. It's going to shrink. It's going to compress vertically. And if your a is bigger than 1, or it's not a fraction basically, then your graph is going to expand vertically. So these letters, they're placeholders right now, but these describe how our original parent function, f of x equals 1 over x, how it changes. Okay, so let's look at an example. Let's check out number 5. Alright, we've got the function f of x equals negative 2 over x minus 1 plus 2. We remember that the parent function looks something like this. F of x equals 1 over x. Okay, so how in the world did this parent function get changed to look like this function? Well, let's identify some key ingredients. Let's talk about that a position first, negative 2. So first of all, since it's negative, I know that the graph is reflected. Across x-axis, since it is negative 2, the a is negative 2. That negative 2 also tells me that it's vertically expanded. Vertical expansion. Since the absolute value of a is bigger than 1, right? If I plug in negative 2 right here, negative 2, the absolute value of negative 2 is 2. 2 is greater than 1, so that causes a vertical expansion based on our rules up here. Expanded vertically when absolute value of a is greater than 1. Okay, looking at this graph as well, what happened here to my x minus 1, that means our graph gets shifted to the right one place. So graph is shifted right 1, which basically means our vertical asymptote, so our VA, is at x equals 1. We can actually go ahead and draw that in right now to our graph. So this causes a vertical asymptote at x equals 1. So I can draw that all the way down. Okay, and then the last thing that we want to check out, this plus 2, that's our k value. That's our k. So the graph has been shifted up to, and that causes a horizontal asymptote at f of x equals 2. Okay, so let me go ahead and draw that in. F of x equals 2 means we have a nice vertical asymptote right across the 2. Okay, with all that information, we can actually graph this thing. We can just do a rough sketch. Now I know that the original f of x equals 1 over x, this parent function, remember it kind of looks like this. I'm going to draw it and then erase it. It goes like this. It would follow along this way, and then, you know, kind of move towards your asymptotes as you go towards infinity, in both directions, positive and negative infinity. But here, remember, we reflected it across the x-axis. But since our x-axis, actually our horizontal asymptote, if you will, remember it starts out here at f of x equals 0, it got shifted up to f of x equals 2, we're actually going to reflect my blue lines here, or the function itself, over that horizontal asymptote. So it should instead look like this. That got flipped over that line, and then up here we can also flip it through. Okay. And this is a good sketch of our function, f of x equals negative 2 over x minus 1 plus 2. If you want very specific points, remember you can always, when in doubt, table it out and get some x values, plug in some x values, get out some f of x values. And then I'd also advise you guys to plug in this function right here, and any of the functions from your homework, into Wolfram Alpha, Desmos, or your graphing calculator to kind of double check and see if you've got this graphing thing down. Alright, we'll get more practice in class, and see you next time.